Welcome to today's webinar, the second part of the webinar, timber beam and surface structures. Last week I modeled the hull, the timber hull, and at loads and load combinations. And today Bastian Kuhn will design the structure. My name is Andreas Hörold, and Bastian Kuhn can introduce himself.
Yes, my name is Bastian Kuhn. I'm together with Gerhard Rehm, who will answer your questions during the webinar, are responsible for the design add-ons related to timber in our company. And as Andreas already announced, I will design the structure that he modeled last week.
Okay, thank you, Bastian. I think we can turn off our webcams that the attendees can see the full screen. On the right side of your screen you can open a control panel via the arrow here, and then you can ask questions. Gerhard and me will answer you. In the case of that there are too many questions that we can't answer all questions during the webinar, you will get an email after the webinar. The other way is to watch the entire webinar and then email your questions to info@dlubal.com. To the agenda today, first point is the design of the CLT slabs. Then Bastian will design the members and then the connections, all according to Eurocode 5. Okay, that's all from my side. I will hand over the screen to Bastian. Bastian, it's your turn.
All right, thank you. Okay, I hope everybody can see the screen. We used to have small technical issues related to the microphone in the last webinar. So whenever that's the case, as Andreas said, just give us a hand and we will try to react to that. Also in the webinar last week where Andreas modeled this structure that I'm going to design right now, there was the question that it was sometimes a little bit too fast and that the attendees could not work parallel to what Andreas modeled. To this I have to say, okay, that's really not planned. You should focus on what I'm modeling here or what I'm designing now today. The webinar is recorded and you can model that afterwards, but working parallel is maybe not such a good idea. Okay, another question in the last week was what you can do in case you have a rafter and the roof overhang a cantilever, and how you could regard that as Andreas modeled the creeping according for serviceability limit state with a creeping factor for moisture class 1. And in such a case, you would have a rafter with moisture class 2 on the outside and moisture class 1 on the inside. I want to give you a short example what you could do in such a case. On this truss, I will not add a cantilever here, but I will show you what you can do also in nonlinear system where you have a high nonlinear system. Therefore, I would just focus on the beam or the truss in the middle. So, and have a look on this, and I will take a look at the serviceability limit state in the combination 117. So they see in order to regard the creeping, the software increased the load by a factor of 1.6. Andreas mentioned that all last week. And now, how could you do that in case this was a high nonlinear system? Because then increasing the load will not regard creeping correct. And that would work via copying this and reducing the stiffness. That's just one way how you could do it. Therefore, in general data, I will now switch off the automatic load combination, and I want to keep the current load combinations, say OK, and now I can go in here and say, okay, load combination, as I said, 117. Copy this load combination, and I will call it non-linear. Okay, and here I have this copied one. Go edit there, and at first I have to reduce the increasing, so just have it with a characteristical level, and then in calculation parameters, and we're gonna need these options later on also for ultimate limit state. There's a check modify stiffness, and if you activate that, you can reduce or increase stiffness of hinges, materials, supports, for nearly everything that you have in the structure. For our endeavor that we have here, we will now reduce with the vice versa value of 1.6 in this case, so that's 0.625 every stiffness. Press OK, and now when we look at the load combination, wait, we want to see both. So at the load combination 117, you see that you have a deformation there of about 40.7 millimeters with the increased load. So with a factor of 1.6. Okay. So with this increased load, and here when, oopsala, that was too far away. And here in this nonlinear combination, we have the original characteristic value. And if we look for the deformation there, as this is now a linear system, you can like really compare that very easily. And you see you have there the same deformation just because we reduce the stiffness. So this is a way how you could do that, in my opinion, pretty easy for also in case you have cantilevers outside, because then the timber material on the outside you could reduce with the factor of 1.8, which is for service class 2, and then the inside you use the 1.6. So it's just one way how you could do it. There are more options to do it, but this is a way how I would recommend to do that. All right. Yeah, this was just due to the questions that we had last week, and that as they were coming pretty often, I think it is worth showing that to everyone. Now we go into designing. Andreas already modeled here a CLT plate just for generating the stiffness that we would need for the design later on. But what he did not do, and what makes absolutely sense when you model the structure not to do it, was to also generate the stiffness for the line hinges and the releases. So he just generally introduced this stiffness here, but for the ultimate limit state you have to reduce this by a factor of 2 divided by 3, the slip modulus. It is, for everybody who wants to know where it is written, it's in the equation 2.1 in the Eurocode 5, and you can do it similar to what I did before with the serviceability limit state. Just go into edit load combinations here, all right, and then you just check on the ultimate limit state, like every combination of the ultimate limit state, calculation parameters, and again switch on modify stiffness, and in modify stiffness you say the line hinge and the line release we now also reduce by this factor according to the equation 2.1 in the Eurocode 5. Okay, so then this is done, and for SLS we are designing on characteristical level. Yes, that's what we want. Okay, so now you have also kind of generated the stiffness differently for SLS and ULS design, and then you can now go to the add-on module Laminate, what Andreas already showed you last week. He used just the result combination here for the design. Usually you should, for the ultimate limit state in Laminate, you should use load combinations because it's generating stiffness and it just makes more sense. But of course this will take now a long time, and now in any design add-on that I'm presenting here today, I just already calculated the design giving combination, and I will just use that just in order to keep the calculation time less and not to spend hours just watching the screen calculating. I think that's not so interesting for you. You all surely know that we can generate combinations and also calculate them in also in not too long time, but for the webinar we want to reduce it further. So okay, so I found out that the combination or load combination 48 will be the relevant combination for me. In serviceability limit state, I will do that actually similar. For the characteristic combination, I calculated the combination 104. This one, I assigned it with a characteristic. I will get to it that point directly. What that means, just I want to introduce all the other combinations. For the quasi-permanent situation, as we are designing according to Eurocode 5 with German annex, there you have 3 situations. What you need to verify the deformation on, it may be different in other countries and also annexes, but we are here designing according to Eurocode 5 with German annex. For characteristic level, we can choose both. For quasi-permanent level, both combination, they are also assigned automatically with quasi-permanent situation. And last but not least, the characteristic quasi-permanent situation, I calculated the combination 159 and 164. Okay, so you see here that those combinations are, as I said, assigned to characteristic quasi-permanent and characteristic quasi-permanent. Now what does that mean? When you go to the detail dialog of the standard here, you can see that the only thing that we are doing, we are using these combinations and are comparing it with the limit deflections that you can introduce here. So it's the length divided by 300. That's actually the only secret what it's doing. Okay, I think the rest was well explained by Andreas already. Maybe we lose a small word on the detail dialog. Here the stresses that are verified in this add-on are predefined also according the German annex of the Eurocode 5. In case you have a wall that you want to design, there are more checks that you should or a wall with wall loading behavior, then you should also activate also these further checks here, but it's then something more special. In the structure that we are designing here today, we just have a plate or loaded plate in this case. Okay, material characteristics. Andreas chose a plate from the producer KLH. Just to introduce all the other producers once again. So we have here also producers like Södra, Steiko, and so on. We try to keep the producer database actual, but yeah, it makes sense to have a double check with the producer just in case he changed some of his setups or some of his factors. But yeah, in general, we try to implement here every producer according to technical approval from the producer. Okay, so we choose the KLH. I'm not going to change that today. Here, edit the details was also shown. KLH uses timber without glue at narrow sides, at least for the stiffness. That's what I said. In case you have a wall loading behavior, you should activate the membrane design here. All the factors are predefined according to technical approval, and this generates us this stiffness here. Also the strength, it counts the same there as well. And load duration and service class is also assigned. Once again, in case you have a rafter with a cantilever, also for the strengths you must choose a different service class. That can be done quite easy here. I mean, we are completely in service class 1, but for the strengths you could choose different surfaces with different moisture class. That's no problem. All right. And then serviceability limit data. Okay, we just have this one surface here, and we want to verify it to the shorter length here, which is from this point to this point 4 meters and 50 centimeters, and we assign it to a displaced parallel surface. I hope these pictures here describe it quite good. Undeformed is just an undeformed system, and displaced parallel surface means that the whole structure can deform, and we are only verify the deformation from one node to the other. All right, then we calculate it. And that gives me the chance to look if there were any problems. Oh, some audio was gone, but it was just by one person, so I hope that is okay. Okay, so for the stress design, we have now a ratio of 42% loading, and it is tension compression, which in this case comes also from bending and tension compression on the outer sides. If you go to the graphics, maybe we can switch off the rendering, yeah, so that helps it. You see that you have pretty high loading in case where the support in the middle is of it, and there are probably also shear problems on the edges of the surface, which also makes sense. So 42% is not loaded that much here in this case, but you also have to take a look on the deformation of the structure, and this is verified here. And so if you look here, you see that for tension, for deformation, the loading is even higher, so we have a loading there of 75% in this case in the characteristic situation. And you should then also not forget, maybe you would need deflection analysis as well, just in case this is required. Okay, so but then at all the design for the beam is done here, or for the panel is done, and we could go to the design of the members. Maybe one thing that I forgot, it makes sometimes sense to get one of these pictures, for example, to the printout report. You can do that here directly in this column. Maybe when we get a nice shear, yeah, this one is probably something you would also want to add to the printout report as well, and maybe something outside the graphics. Yeah, this one, for example. So the design of the plate is done with this, but the connection there on the edges of the plate and also on the outside of the plate needs to be done, and therefore we will just grab the combination 48 in ultimate limit state. 48, 48, there it is. And here in the result you have down below the option releases, and there you can see what normal force you have in the line hinge. Okay, that's not so interesting here, I think, but for the plate lying on top of the beam, it's probably relevant, because this is the shear that's in between the plate and the member, and that's what you really need to connect. And you see that there the value is not that low, and that's something you probably need to verify. So this gives you a good graphical overview. Via right click result diagram, you could also smooth around this area. So you see here, you have here, well, it's not a really high peak, but you can say, okay, my connections go, for example, over 1 meter. And if you say, okay, I'm starting at 1 meter and ending at 1 meter, and then I want to have a linear or constant value, you can also smooth it a little bit, so you have a value, I hope you can see it, of 10.8 instead of 15.35 kilonewton per meter. Okay, so but then when you have done this all, the design of the plate with its connections is done. So you could say check to this, and now we go to the members. Therefore we will start the add-on Timber Pro. And in here we have members and set of members. Set of members in our constellation that we have here are important for the serviceability limit state. So for the deflection, I will only verify the set of members in the middle, so the set of member 9 and the set of member 6. You see, and the set of member in this case is, set of member is also important for stability, but in what we are doing here today, we are taking the deformation from the point where you see the mouse here and the mouse there, and so we take the whole length and verify the deformation on this part. So that's what we do here. Once again, also here I will not verify the complete result combination, as this would be too time consuming now for the webinar, and I will use the combination 38 and 44 just to have 2, and I will do the same for serviceability limit state with the combination 72. Oh, come on, for the characteristic level. Once again, for quasi-permanent characteristic, I can choose both, as there are only 2 generated, and for the characteristic quasi-permanent, this one now, I will use the combination 164. Okay, once again, it's similar to what we have had in the laminate add-on. It's automatically designed. If you want to do a simplified vibration design, you could do that here as well. But for the members, I don't see that too problematic here. Maybe for the CLT, as I said, that would be something I would maybe do or add, but we're not going to do that today. Fire resistance is possible with Timber Pro. It is also possible with the laminate add-on, but it requires more effort. Maybe Gerhard or I will send you an FAQ where we answer that. So it's possible, but in laminate, as laminate generates stiffness, it is just more effort to do. Nevertheless, it makes sense to take a look to the detail dialog of the National Annex, because you not only can define deformation limits, but you can also add all the other factors, for example, for K-crack, for shear, verification. If you, for example, want to calculate LVL from the producer Baubuche and so on, you could also activate that here in the detail dialog. The rest is not so important. Load duration service class is also the same dialog as what we have had in the laminate add-on. One thing I forgot when we started it, in this case we defined imperfections and calculated the ultimate limit state according to second order theory. Therefore buckling does not need to be verified, and lateral torsionally buckling, I say I have a pretty stiff sheeting and I will verify that separately, and therefore I can switch off the whole check for the stability. Serviceability, that's the same as what we have had in laminate. With deformed and undeformed system fire resistance we do not do here. Okay, that's this. Serviceability data, okay, we say set of members. I remembered what we did there. Member 6 and member 9. So the ones in the middle, and I'm using the full length. And maybe also the members underneath the CLT should be verified for deformations. I will now only take the one here inside. Maybe I just don't care about the ones on the outside, and verify them. All right. Parameters is shear force reduction and also cutouts, what we do not have in this situation, and so we could start the deformation. We could start the calculation of all the combinations that we could that we assigned. Okay, there was a question for the fire resistance. Okay, maybe I just quickly can introduce that a little bit more. I will not verify it today, but just to keep you informed to that, in order you want to verify fire resistance, you must create an extraordinary combination in load cases and combinations. And then what we do is just that we reduce the section or all the sections inside here with the so-called burning rate. And according to this burning rate, we do all the verifications for the ultimate limit state again with the reduced section. So in general, it's also not so fancy to show, as it is actually the same as what we have here in ultimate limit state. Okay, hope that explains it. And we also have FAQs. I'm sure Gerhard or Andreas will also send you, or I will send them to you afterwards. Okay, but we have now here a pretty big problem, because we have an overloading of 43% according shear force and torsion. So torsion is really a problem according to Eurocode 5. When you design deformation, that's all fine. I'm loaded 80% here, but torsion is a problem. So where does that come from? If we go to graphics and look for it, and you can see that it's just on the edges of this beam here. Maybe I will just work with the reduced view. So you see that it's only here in these edges. And where does this come from? Okay, maybe we look for the combination 38, where we have calculated that. 38. And then the inner forces there and the torsional moment, which is the critical point here. In members, torsional moment, and maybe we switch off the releases. So, and you see that we have here a torsional moment of 4 or nearly 4 kilonewton meter there on the edges. And it's clear we forgot to put the degree of freedom here. It's only the degree of freedom, the degree of freedom for the moment in Y and Z direction, but not for torsion. So the phi x on these edges needs to be also given the degree of freedom of 0, which is always the case in timber design. Yes, that requires that I delete the results. Because a moment of 4 kilonewton per meter, you would never or hardly can be transferred with any kind of connection type that we have there. And we will do actually the same here on the start. So member start, this one as well, so the same hinge there. And now when we calculate the combination 38 again, and just look for the torsional moments that we have now, you see that we like really decreased the torsional moment by a high amount. And now when we go back to the design in the add-on, we keep the serviceability limit state. It makes maybe not so much sense here, as we saw that the serviceability limit state was not really a problem, but maybe we want to see the deformation in the longer set of member. There, I want to show you also the graphical presentation of that. And now you see we do not have any problem now from the ultimate limit state, and design giving is now serviceability. All verifications are listed here, and you can like recalculate everything that's done by the add-on. Okay, as I said, if we go switch to graphics and to the whole structure, we switch off ULS, and you see that, yeah, like the longer beam in the middle was actually what I expected, is design giving with a loading of 80%. Okay, yeah, and the smaller ones are also loaded pretty high, the beams that are underneath the CLT plate. Okay, that would be the design of the structure, and we can calculate now the connections. I want to concentrate on the connections here at the outer edge of the hall, and also if we have the time left to the connections between the column here and the beam that's spanning from this point to this point. But at first I want to design the edges, therefore I will start the add-on RF joints. So that's yeah, it's a little bit different to what I showed you in the Timber Pro and in the Laminate add-on, because in this add-on here we have the possibility to design steel and timber. These are all different add-ons. So we are concentrating today on timber, and then also in this add-on you can still separate between steel to timber connection and timber to timber connection. Steel to timber connection is every indirect connection where you have a steel plate sliced into your structure, and timber connection is a connection between main and secondary truss or load bearing. So we will concentrate for this corner here on steel to timber connection. You can calculate dowels, bolts, nails and screws. We will design dowels. You have the option to design different joint types. Our joint type will be without continuous member, because we will just have two members that are connected in here. You can choose the cutting main area, how they are connected. You can, similar as I actually skipped that a little bit in the other add-ons, you can choose the standards with all the national annexes. For Eurocode in here, the detailed dialog is pretty similar to Timber Pro and Laminate. You can calculate dowels from the company SFS that can be screwed. They're a little bit special in their behavior. You can also do a simplified fire resistance check, where we just calculate if it's covered or not. But once again, it would require an extraordinary combination, what I did not do, or we did not do in this situation here. You can check the contact of the members and also calculate groups of doubles. All right, then we go into the structure, and therefore we will select, right, let me switch off the rendering again and also the results. And so we will calculate all the corners here with one check, and also the ones from the other side. All right, so now I get a lot of alerts in here, which is clear because we have invalid members, because yeah, steel rods cannot be designed with a steel plate, and also the secondary beams here do not make too much sense. So we will just keep the connected member and the main member, and all the other members we will set as inactive. So this one inactive and this one as well. And then it asked me, okay, shall all the other connections work similar to this? Yes, that's what I want. And do you want to have default geometry? No, I do not want that. Okay, now all these nodes have the information that they should be connected in here. Once again, I will just assign one ultimate limit state combination, so 13, or let's say 2, 13 and 19. Load duration and service class I will just skip. I don't think that's too important. And now we are in the dialog of the geometry, and that's now the important dialog. Here you can at first define the shape of the steel plate. User means that it's just assigning the steel plate on the outside edges of your structure. You could also have it rectangle. I don't think that will, here you see. So then it will be a rectangle one, and it could also be convex. I think user for most constellations is the one that you would want to have. You can define up to 5 sliced steel plates. For our first design approach, I will assign 2 steel plates. I will give it a thickness of 14 millimeter, and everything else I will leave as it is. We can also define side plates, but I don't want to do that for doubles. It's probably not so sensible for nails and screws. It makes maybe more sense. We can choose a pattern, rectangle or round, or circle, sorry. And here we define the diameter of the dowels. I keep them similar as the plate with 40 millimeters. And I say I want in X direction 8 dowels and in Y direction 4, and maybe also want a more sensible limit distancing with user-defined limiting. So for the main member, I will choose a one of 100 millimeter and a 2 of 175 and a, oops, that was too quick, A3T by 140. Okay, so that's that. I have to do the same for the connected member. So that's 14, so 8, 4. And also here I make a user-defined distancing with 105. I could save all this this group to a library and just get it back again. So that's also possible. I do not have to define that every time again and again. Now talking and inputting is too much. So A2, I define a distance of 160 and A3T a distance of 130. Yeah, this is this. I could also reinforce the screws, but I want to look if this is really necessary in here. And when I have bolts outside, I can avoid the bending side of the members. So these are more options that I have. And now when I calculate it, what did I choose now? 19 and 30. 13, sorry. Right. So, and now we see here that it's overloaded by 5%, but we also see that the steel plate is like loaded nearly nothing, 7% loaded. The dovels itself, they are loaded by 42%, so that's also not that much. But in the verification of the dovels, you can see that we are verifying the force in each dovell. So we really get the force that we have in, and also the deformation that we have in each dovell in here. And you see that we have an overloading by shear of the timber. So the timber is overloaded. And now what can you do when you have an overloading of the timber? According to Eurocode, you should calculate with the regarding of slip in the connection. Right now, when you look outside the structure, wait, we can do that in here. There is still this connection now assigned, okay, for sure. But it is still this moment hinge here with a value of 0, and it's, but this beam or this member is connected to the corner point. But if you look for that more detailed, you would say that it's probably connected via all the dovels, and here is actually no connection. So the static system that we are designing in here is actually wrong. And now this add-on gives you the possibility to generate the member eccentricity and also generate the connection model. And now if you activate that, it asks you that it will delete all the elements, and it will also create a new static system. So if you look for the back of the screen right now, you see that now that I pressed OK, it overrides every element that I have activated in here, and it kind of loosens. Wait, I have to go outside, and maybe we will just look for the truss in the middle again, just like we did in the start. So, and if you look for the combination 13, I think that was the design giving. 13, and let it calculate. In here, okay, the joint is not so relevant here, but when you look for the deformation, I think that's probably the most impressive thing to see. You see that there is no connection anymore, as the connection goes now from this point to this point. So that's the intelligence behind it, according to Eurocode 5. So, and with this information, we go back to the design tool. We saw that we had a pretty low loading of the steel plate. So to me, even with now a higher loading of the connection, but because usually when you calculate with this slip in this connection in here, you have a lower loading of the timber but a higher loading of the connections. That's what you really will find out. But the steel plate was only loaded 7%, so 2 plates probably make no sense in here. And therefore I changed that to 1 plate because I think it's still enough. But I probably have to increase the diameter of the dovels. So I keep that now with 18 millimeter, and I do the same for the main member just to have it similar. Everything else I leave as it was and calculate again. Now it asks me again, okay, that means I have to change the stiffness because I changed diameter, and the stiffness exported right now was according a diameter of 14 millimeter. And calculate that again, and I hope, I cross my fingers, that now the loading or the overloading of the timber is not a problem anymore, hopefully. But I expect problems in the connection design there. So, and you see now we have an overloading of 12%. Damn, that's actually not what I wanted, but let's have a deeper look into it. So the doubles are now loaded like nearly 50% more. Steel plates also loaded pretty much more, but the timber is now not a problem anymore, but here the connection is a problem. Okay, what else can you do if you do not want to change the geometry? The main member was actually okay. Maybe the connected member is something what you could try to improve, and that's what I said when I started the add-on. You could reinforce it by screws, for example. So, and if you want to do that, maybe I define it manually. I am not want to increase the length of the screws to near the outside of the beam. I can just extend it by 10 millimeter, and if I'm choosing a screw from Word according their technical approval, I can assign a strength of 12.5 and maybe also say, okay, I avoid the bending side of the members. That would actually require also some screws on the outside or a bolt, but just for giving it a try, and I mean a bolt is also possible in here as well. So I saw there was a question about EFC and BIM, building information modeling. That's not part of the webinar today. Probably Andreas will make webinars with this pretty soon, or we already have probably webinars he can send you. Okay, got the result. We have now success. Everything's below 1. We have the green hook here. So, and we have now only 96% loading of the dowel group. That's what we want. Here in geometry, you can see actually the stiffness similar to what I did with the connections in the laminate in the CLT plate. It does it similar or different for SLS and ULS situations. It's the same equation, 2.1. According to Eurocode 5, and exports that for every load combination differently outside. You can also have a DXF or a plot you can export, maybe when you just want to export the plate to something. You can also export to your CNC and create a shop drawing of it as well. Okay, yes, we can check connections also for fire. I said it when I introduced it, but with simplified approach. Okay, we have a few minutes left, and I can actually take the chance to show you now maybe not the connection or the foundation design, as this was a question here, but to show you where you can do it, because I wanted to connect the beams here from where the CLT panel plates are supported on to the column, and also the footings or the foundations of the columns. Just let me look what combinations I want to verify. It's the combination 48. This here is the same as what we had. I do not get into details of that anymore. And now if you go into limit description in here, you see that this actually is a pretty big database where you can verify everything that has a limit strength. So we have here different object type, member type, members, nodal supports. That would actually be the thing you would need for your foundation. So you could also say, okay, I'm verifying. You see it already here that the combination 30 would probably not be enough for this footing right here now. And we have several producers in here from Shiga, Sherpa, and so on. And you can also create your own new limits in here. just whatever you want. And you can also verify the same point for member end with joist hangers and so on. We also have there several producers implemented, Wood, Simpson, Strong Tie, and so on. Actually, I want to choose the Shiga connector now today, but there are others as well. And you see we can check the section dimensions and also the load. Here we can define the list of members. I once again will just take the inner ones, or the members that are on the inside of the structure, start and end member, say OK, and say OK, service class, and service class in this case is 1. Factor category, I can use solid timber. I can optimize this according the row or the group and so on. Load duration class, probably there's not really much to say. We've had that all. Medium term is the one that's chosen here for the combination 48, and then verify this as well. All right. So, and you see in here, so as I said, this is the database. It will check if the section is correct, or if it's possible to put this connection that we chosen here on this section that we have, and also if all the minimum and maximum values are verified. So this is it, but it's probably quite handy to check a complete structure pretty quick. And you can, as I said, you can do the same for the foundations, but I'm not going to do that today. All right, then I would say point. All right, at the point, and I would like to thank you for your attention and give the word back to Andreas.
Yeah, thank you, Bastian, for the nice presentation and that you showed the add-on module of limits spontaneously. Yeah, I thank you all for the participation of the webinar. Thanks to Gerhard for answering the questions. Yeah, and just take care and bye-bye.
Ciao, thank you.